Next, we're going to look at electron configurations and periodicity. This is chapter 8. We'll start with looking at electron configurations for atoms that have more than one electron. So we're looking at many electron atoms. Because as you recall, the solution to the Schrödinger equation and the Bohr model of the atom was mainly for the hydrogen atom. And what we're going to do with respect to many electron atoms is we're going to use the same orbitals as for the hydrogen atom, meaning we have the same shapes. So if we know an s orbital is sort of a spherical shape and a p orbital has these lobes, same shapes are going to be applicable here. So the one thing to remember is that in the hydrogen atom, the energy of the orbital depends only on n. On the principal quantum number. So for example, this is a figure 7.21 from your textbook. So this is from last chapter. But we could see, so here we have the energy, we have the 1s orbitals, the 2s and the 2p. For all of these orbitals have the exact same energies if we only have one electron in the atom. Okay, so in other words, the 3s, the 3p, and the 3d all have the same energy. What we'll see in a moment is that for many electron atoms, the subshells have different energies. Because of electron Coulombic repulsion. So what we're going to see, and we're going to see why this is the case, but why is it that the 2s and the 2p would have in a mini electron atom where we have so if we have electrons in all of these, what are their energy levels going to be? And so on for the 3s and the 3p again. So we'll see exactly how that looks if we start to put more than one electron into the atom. All right, now there's something that I alluded to last time, and that is that an orbital can hold at most 2 electrons, but only if they have opposite spins. And this is called the Pauli exclusion principle. It quite simply says an orbital can hold at most 2 electrons, two electrons, but only if they have opposite spin. Okay, and so remember electron spin can either be plus 1/2 or minus 1/2, and what this has to do with is this. It's something. This is a figure from your text. It has to do with how an electron reacts with a magnet. Okay, spin is a strange intrinsic property of matter, and electrons can have plus 1/2 or minus 1/2 spin. Now, what the Pauli exclusion principle is really saying is that in one electron, in one atom, no 2 electrons can have the same set of 4 quantum numbers. So another way to put this is that you can think of it as being every single electron is uniquely defined by a set of 4 quantum numbers. So opposite spins allow electrons to occupy the same orbital, but they're two different electrons, so they have opposite spins. Okay, and so essentially every electron has a distinct set of 4 quantum numbers within a particular atom. Okay. So electron configurations and something called orbital diagrams. Okay, so let's think about electron configurations first. So we're going to do this. We're going to designate the orbitals occupied by the electrons in the atom. And the notation will look like this. Principal quantum number, azimuthal quantum number, is given by the letter, right, designation. And then we're going to put up here in superscript the number of electrons. This is called the configuration. Okay. We can use, so that's an electron configuration. And we'll see exactly how this works in a moment. We're going to use orbital diagrams to show the arrangement of electrons within the atom. Okay, so of course, in a neutral atom, the number of electrons equals the number of protons. So for example, if we have a hydrogen atom, we have 1 proton. It would have a single electron in it. That would be a 1s1 electron. And then an orbital diagram is going to look something like this. So there are a number of ways to draw these. Your book uses circles with arrows in them for the electrons. I typically use lines with arrows for the electrons. And so what this is saying is that there's a single, this is the 1s orbital, there's a single electron in that 1s orbital. If we go to helium, the electron configuration is 1s2. In other words, we have 2 electrons in the 1s orbital. The 1s orbital would have 2 electrons. And to indicate that they have different spins, meaning they have a unique quantum address, if you will, right, by the Pauli exclusion principle, we're going to draw the arrows 2 different directions. We can go to lithium, for example, and in this case we'd have 1s2, 2s1. We'd have 2 electrons in the 1s and 1 electron in the 2s. Now it doesn't really matter if the first one you put in is up or down. As long as you have 2 different spins, meaning arrow directions, for every single atom. If we go along to, say, for example, carbon, the electron configuration would look like this: 1s2, 2s2, 2p2. We'd have 2 electrons in the 1s 2 electrons in the 2s and 2 electrons in the 2p orbitals. Okay. We don't distinguish m sub l values because they have the same energy in the free atom. Okay. We do not distinguish m sub l values, same energy in the free atom. The text uses circles for orbitals. That's fine. Whatever works for you to be able to, whatever works for you. Okay. The next thing we're going to look at is we're going to look at exactly, well, how did I know what the orbital diagrams were for a given atom? And to do this, what we will do is we're going to use something called the Aufbau principle, or the building up principle. Okay, and what we'll do is this, we have the ground state electron configurations, or what the building up principle gives us. Ground state electron configurations. What ground state means is the following. What it means is that it is the lowest energy configuration. The lowest energy configuration. Okay. And we'll look at this again, but it's the lowest energy configuration means ground state. If you're not in the lowest energy configuration, you're in an excited state. Okay, but first we'll look at just some terminology and so on. What we have is the following. We're going to, for many electron atoms, orbital configurations depend on n and l. So principal quantum number and the shape, quantum number. Okay, so the energies are going to depend on both of those. Well, and sorry, the orbital, I apologize, the orbital energies depend on n and l. I'll give you a second to correct that. The orbital energies depend on n and l. And what we're going to do to figure out what the ground state configurations are is the easiest way to do it that I know of is to follow the periodic table to write electron configurations. Okay, and what we have is this. And I'm going to use a periodic table that you probably have or you could get, and I'm going to make notations on it to show you what's going on. This is similar to figure 8.9 in your text. Essentially what we're going to do is we're going to create that figure in your text. When we have the representative elements, remember the representative elements are here and here, right? These are the representative elements. What we have are the s orbitals and the p orbitals that are going to be filling. With the transition elements here, what we have are the d orbitals filling up. With the lanthanides, those are the 4f orbitals filling. And here with the actinides, we have the 5f orbitals filling. So here we have the f orbitals that are being filled up. And what we're going to do to be able to write these configurations is the following. And I think there are a number of ways to do this, to be able to do this. But let's say we wanted to, say, for example, find the electron configuration of oxygen. The electron configuration of oxygen is going to be the following. What we have is this. So this is going to be 1, 2, 3, 4, 5, 6, 7. Okay. This represents the 1s1 configuration. We add another electron, and we have so this is the s orbital there that's filling. But so I know it's a little weird, but so 1s1, 1s2, and then what I'm going to do is go down here. So if we wanted to get to here to the oxygen configuration, we're going to start at the beginning. 1s2, that brings us to the electronic configuration of helium. 2s2 electrons brings us to the electronic configuration of beryllium. And then 2p, 1, 2, 3, 4 would be brings us to the electronic configuration of oxygen. So oxygen, 8 protons, 8 electrons. This would be the ground state configuration of oxygen. You'll see what we did here. This is table 8.1, but these are the ground state electron configurations. Oxygen. How did they get this? Well, they did exactly what I just showed you. Use the periodic table to fill the electrons as we go. That seems to be a relatively straightforward way of doing that. Let's do another one just to see what's going on. Let's do, for example, manganese. Manganese 25. So we want the electron configuration of manganese here. We're going to start here at the bottom. Okay. 1s2 brings us to the electron configuration of helium. 2s2 brings us to the electron configuration of beryllium. 2p6 brings us to neon. 3s2 brings us to electron configuration of magnesium. We're in row 3. This is the p. These are the p orbitals that are filling. 3p6 are filling there, right? And now we have the same electron configuration as argon. Now we have the 4 s orbitals that come next. And this is where it gets a little strange. If you recall, we went, the principal quantum number 3 can have s orbitals, p orbitals, and d orbitals. And so the d orbitals start to fill with this first row here of the transition metals. So this would be 3d, and we're going to count over 1, 2, 3, 4, 5, would be the electronic configuration of manganese. And this is the same thing that we have here. Here they've just grouped the 3 Ds together rather than the 4 S's. It doesn't matter which way you write them. There will be some consequences later on that we'll learn, but that will work fine. So using the periodic table to do the Aufbau principle is to write the electronic configuration is a relatively easy way to do it. Another way to do it, which some people like, is the following. They like to do something like this. It's a mnemonic that people use to be able to, the 1s orbital, the s orbitals, you stack them up, and then the p, d, and so on, and then they fill going in this direction, and then you know which comes first, and you can see it works well. The 1s, the 2s, the 2p, the 3s, the 3p, and then the 4s, then the 3d. And it's exactly like we just did by using the Aufbau principle here to write the electron configuration. Okay, now finally, and I know that this is going to take a little practice to be able to do this, but I'm sure that you can do it. All right, with respect to, and And so actually, let me show you figure 8.9 in your text, which has the same thing that I just showed you. So here we have, for example, manganese. We have here they're only showing what are called the valence electrons. We'll look at that in a second, but 3d5, 4s2. So these have the s subshell fills, the d subshell fills, the p, and so on. Okay. Now, just a little bit of terms that we need to be able to use. With respect to the Aufbau principle and electron configurations. Something, and I already talked about this, the ground state electron configuration is the lowest energy configuration. We're going to fill orbitals, and orbitals fill in order of increasing energy. The excited state, or something called an excited state, is where electrons can be promoted to higher energy levels. So anytime an atom has electrons that are not in the ground state, we would say that it's in an excited state. Finally, valence electrons are electrons outside the noble gas or pseudo-noble gas core. Another way to put it is that, a better way to put it actually, and what I mean by the noble gas core is the following. You'll notice that, say for example, neon and argon have all of their s and p orbitals that are filled up, right? Helium has the s orbital filled up. All of the s and p orbitals are filled up with electrons. That's called a noble gas core. Another way to think about a valence electron is even easier. A valence electron are those electrons with the highest n value. That's the easiest way to think about it. And then we have opposite of valence electrons, anything that's outside of the highest n value. Are called core electrons. Another way to put it are they would be inner electrons or non-valence electrons. Those are some terminology that we'll be using as we go here, and we'll look at some of these things as we go. One final thing is about this there are some exceptions to the building up principle. And that is that filled and half-filled subshells represent especially stable configurations. Okay. Exceptionally stable configurations. So, for example, one example might be, what I'm going to do is use this figure 8.9 again. And we have, for example, this is what I'll do. Filled and half-filled subcells represent extremely stable configurations. So, for example, we might have, when we have neon as an example, we've filled the S and the P, and the noble gases then are extremely stable. Something similar to that might happen in a case such as this. Let's say we have chromium. chromium has an electronic configuration of 3d5 4s1 rather than 3d4 4s2. Let's look at chromium on the periodic table that we were using. Chromium is right here in the periodic table. And if we were going to write its electronic configuration, we'd start at the beginning. It would look like manganese's, right? So we'd expect it to be up to 1s2, 2s2, 2p6, right? Just like that. 3s2, 3p6. And what we might expect is that it would be 4s2, 1, 2, 3, 4, 3d, 1, 2, 3, 4, right? This is what we might expect. 3d4, 4s2 from what we have just following the periodic table. But what happens is this, is that chromium is actually 3d5, 4s1. So what happens is an electron is taken from the 4s and the 3d orbital is then half filled, and it's exceptionally stable. The same thing happens with copper. Copper is 3d10 4s1 rather than 3d9 4s2. Copper would be 29, 3d10 4s2 rather than 3d10 4s1 rather than 3d9 4s2. Copper is here, 3d10 4s1. So an electron is essentially taken from the 3d orbitals, or from the 4s, the electron is taken from the 4s and put into the 3d, so then we have a filled subshell. And the reason this happens for these strange cases comes around because of this. Now, if you recall, for the hydrogen atom, this is figure 7.21. For the hydrogen atom, all of the subshells and shells have they're degenerate. They have the same energy. It's called degeneracy. They have the same energy, and so they're all the same. When we start to put more than one electron into these, what happens is we end up with differences in the energies of the subshells. And as you can see, as we get higher and higher in energy, the differences in the energies becomes less and less. And the difference between the 4s and the 3d is very tiny. And so it takes very little energy for the 4s electron to come and populate the 3d orbital. The atom essentially gets energy by doing that, by taking an electron from here and making a filled or half-filled 3d orbital with chromium and copper. We'll continue our discussion of electron configurations in the next segment.